Look at this digital grid. When one central node freezes, it causes a cascading traffic jam of light pulses. This is the exact mechanical failure faced when synchronizing data from operational databases to downstream services. If you extract data the wrong way, you degrade the primary application's performance. The oldest extraction method is batch processing, or pulling. The downstream system repeatedly queries the database, asking for new rows. This guarantees data staleness and triggers sudden, massive CPU spikes whenever the batch job runs. To solve staleness, engineers often rely on database triggers. Triggers fire immediately when a row changes, but relying on them embeds hidden business logic directly inside your database storage layer. This split-screen CPU latency chart isolates the mechanical problem. On top is a healthy write flow. On the bottom, a write blocked by a red trigger node. Because triggers operate synchronously, the primary write request is forced to wait until all secondary tasks are completed. Introduce routine schema evolution, like dropping a deprecated column, and triggers written years ago will silently fail. Your critical production flows break, and the source of the error is entirely obscured. These legacy synchronization methods are inherently parasitic. They penalize the operational systems they attempt to monitor. Moving past synchronous blocking requires a different strategy: change data capture, or CDC. This architecture diagram illustrates the foundational mechanism of CDC. Write operations land in the main table, but the database also appends them to a parallel transaction log file. A separate process reads exclusively from this log, extracting data with zero interference to the main table. These transaction logs natively capture every insert, update, and delete in strict sequential order. They provide a flawless, row-level audit trail of state changes. Today, we will build a production-grade, serverless CDC pipeline on AWS. We will route these raw database logs directly into an analytical data lake. When you implement CDC, the database announces every change as it happens. This effectively isolates extraction logic from the high-pressure environment of the operational application. Here is our architectural blueprint. Node 1 is a standard relational database, like MySQL or Postgres, emitting a continuous stream of raw change events. We connect that to Node 2, AWS Database Migration Service, or DMS. Configuring DMS in ongoing replication mode forces it to act as a CDC engine, reading the source logs and converting them into standardized AWS events. DMS is a managed instance, meaning you must size it accurately, starting with a compute-optimized instance like dms.c5.xlarge. You also must isolate it within a VPC to securely read the source logs without exposing traffic to the public internet. If your source is a NoSQL database, you use a different ingestion pattern. By enabling DynamoDB Streams, the table itself automatically pushes item-level changes as a time-ordered sequence. This bypasses the need for an ingestion server like DMS entirely. Whether using DMS or native streams, the ingestion layer's primary duty is identical: translate raw database logs into a standardized stream without dropping a transaction. Those events flow into Node 3, Amazon Kinesis Data Firehose. This is our delivery stream. It receives events from the ingestion layer and pulls them into a buffer block. Firehose's buffering logic dictates a specific trade-off. You can set a short buffer, like 60 seconds, for low latency, or you can set a large buffer, up to 900 seconds or 5 megabytes, to batch records tightly and reduce downstream S3 API costs. The records arriving in this buffer are raw CDC data. They are formatted as highly verbose, nested JSON. This is inefficient for analytics and requires in-flight transformation. To fix this, Firehose invokes Node 4, AWS Lambda. Watch how the nested JSON payload enters the Lambda compute node and is instantly flattened into a clean, two-dimensional tabular structure. Lambda applies this transformation in flight. It flattens the schemas, filters out internal database metadata, and applies data type coercion. But there is a danger here. If Lambda encounters one malformed record and returns a failure, Firehose retries and eventually fails the entire batch. To prevent this, you implement a dead letter queue pattern. Lambda must be programmed to mark individual bad records as processing failed and route them to a separate queue, allowing the rest of the healthy batch to proceed to storage. The buffer and compute layers act as the pipeline's shock absorbers. They scale to absorb unexpected traffic bursts, ensuring only sanitized data progresses forward. The transform data lands in Node 5, Amazon S3. Notice how the incoming files separate into distinct directory folders labeled by year and month. This is dynamic partitioning. Grouping data by attributes, like table name and date, ensures downstream analytics queries only scan relevant files. This drastically cuts scan times and computing costs. S3 now holds highly organized raw files, but analytics tools cannot query these files without a defined schema. To solve this, we introduce Node 6, AWS Glue. A glue crawler periodically scans the S3 partitions to discover schemas, extract column headers, and register them as a structural blueprint in the Glue data catalog. Glue also manages schema evolution. If a developer adds a new column to the source database, the crawler detects it and automatically tracks the new table version, preventing your downstream queries from breaking. With the schema mapped, Glue ETL Spark jobs process the raw stream of isolated inserts, updates, and deletes. They merge these events logically to output a single current state snapshot table. Once registered in the catalog and processed by ETL, the CDC data is instantly queryable via serverless engines like Amazon Athena. Without rigorous S3 partitioning and automated schema management via Glue, a raw CDC stream will rapidly degrade your data lake into an unqueryable data swamp. The pipeline we just built is strictly optimized for analytical batching and historical querying. However, operational CDC has completely different requirements. If an order is placed, you need immediate, sub-second actions across microservices, like notifying a shipping team or sending a confirmation email. For operational workflows, the architecture bypasses the batch and delayings of Firehose and S3 entirely. This branching architecture shows it. A source database emits an event that forks. The upper operational branch routes swiftly through Kinesis data streams, triggering a Lambda processor that instantly fans out alerts via SNS. The lower analytical branch routes through Firehose and S3. CDC is not a single rigid blueprint. The latency requirements of your destination systems dictate whether you architect for batch compression or sub-second event fan-out. Moving this to production requires strict IAM least privilege. The ingestion role must be granted permission to write to the stream, but never permission to read from it. You also need precise monitoring. You configure CloudWatch to track metrics like CDC latency source to monitor extraction lag and delivery to S3 data freshness to monitor your buffer health. This is a data engineer CDC checklist. If you are discussing architecture in an interview, present these 3 rules. First, avoid synchronous triggers. They block primary operations and degrade database health. Second, automate schema drift. Utilize tools like Glue crawlers to track table versions, ensuring upstream changes don't fail the pipeline. Third, architect for eventual consistency. Because CDC is asynchronous, downstream applications must be explicitly engineered to tolerate minor replication lag. By orchestrating CDC pipelines, you eliminate the delays of batch processing and build infrastructure that reflects the live state of your source data.